Good afternoon, everyone. Welcome back to another lecture on mathematical statistics. Today, we'll continue our discussion of the continuous random variables. In particular, we'll be focusing on the gamma and the beta distributions. So these two distributions are based on what are known as special functions. So let's first discuss the gamma function. The gamma function, using the Greek letter gamma, is arguably the most common special function. So the gamma function is defined for a positive number z bigger than 0 via the definite integral as follows. So this is the gamma function, and it is, as we say, the definite integral from 0 to infinity of x to the power of z minus 1 e to minus x dx. So if you're home or at a coffee shop, please verify at your leisure that gamma z is a well-defined integral. So by that, what we meant is that you will want to check that the limit as x goes to infinity of x to the power of z minus 1 e to minus x is going to be 0. So what this means is that the exponential function decay to 0 faster than any polynomial of x to the power of z minus 1. So e to minus x decay to 0 faster than any polynomial of x. So a key property of gamma z is the following recurrence formula, which says that for gamma z plus 1, that's the same as z gamma z. So this proposition is problem 4.81 in your textbook. So please take a look at that problem, just for comparison. So this result here is a simple exercise in integration by part. So here we have the integral gamma z plus 1, where now, because we do z plus 1, it's going to be x to the power of z. So now we can just let u be x to the power of z, and then dv is e minus x dx, in which case du is z x z minus 1, and v is minus e to minus x. So therefore, you have here this term uv, and then this term is minus integral of v du. So the nice thing is that uv, you can use the same property here, that it decays to 0 fast, to show that this term will have to be 0. And then this term, you have the z here, which you can move outside, in which case what you have remaining is the integrand for gamma z. So therefore, you have z gamma z. So a nice consequence of this recurrence equation is the following. First, we note that gamma 1 equal to 1. Verify this at home. Then for any positive integer z, we have that gamma of z plus 1 is z gamma z. And our gamma z is z minus 1 gamma z minus 1. So you can add that in. And then gamma z minus 1 is z minus 2 gamma z minus 2. You add that in, and then all the way down to gamma 1, which we say is equal to 1. So you have z factorial. So in a sense, gamma, the gamma function, is an extension of the factorial from the positive integers to just the positive real lines. As another example, this is problem 4.196 in your textbook. You can show that gamma of 1/2 is square root pi by using a change of variable. So here we have gamma z is this term here. So by doing the change of variable, by letting x be u squared, in which case dx is 2u du, you have this is dx. And then now x becomes u squared, so you get u to z minus 1. E to minus x becomes e minus u squared. And now if you let z be 1/2, then this term here will just be u 1 minus 1 is 1. And so what you have left is that gamma 1/2 is this integral. And this integral should be familiar to you, because that looks like the PDF of the normal distribution. So because it's symmetric, you can start from minus infinity to infinity. And this is nothing more than the PDF, the integral of the PDF of x, which is normal, which means 0, and variance 1/2. So check this at your leisure, in which case the answer has to be equal to square root pi. So now we see that the gamma function can be used to define what is known as the family of gamma distribution. So the gamma distribution here is a family of distributions or family of continuous random variables. And this family are characterized by two parameters. Alpha, which is known as the shape parameter, and beta, which is known as the scale parameter. So a continuous random variable x is said to be a gamma random variable with this parameter alpha and beta if it has the PDF given here. And this PDF can be defined for x, really for x bigger than 0. So equality to 0 doesn't really matter. As we see later, many times you may want to not to use the scale parameter, but rather you want to use the rate parameter, which is given by 1 over beta, where beta is a scale. And this parameterization turns out to be more useful for some special case of the gamma. So these two parameterizations are equivalent. Two different but equivalent parameterization. Okay, so check at your leisure that this is a valid PDF. So what this implies is the following very useful fact that we see later, is that the integral of x alpha minus 1 e minus x over beta dx has to be gamma alpha to the beta to the power of alpha. So we will write x gamma alpha beta or alpha lambda to denote a gamma random variable. And usually, because of these two different parameterization, we will usually be very explicit to say that we have the shape and scale or shape and rate. Okay, so let's see. So the key point is that as alpha changes, the shape of the PDF changes. So here's a case where alpha is equal to 0.5 and 1. So this is what you have for alpha at 0.5 and 1. And then as you will see in your normal PDF upload slides, that when alpha equal to say 2, the PDF now will look more, maybe more something like this. And then for alpha equal to 6.72, it will look much more, say, symmetric. So maybe I should make this figure a little bit better. For alpha 6.72, it will look quite a bit more symmetric. So here look a little bit skewed to the left, and now here will look a little bit more symmetric. Okay, so the alpha parameter changes the shape of the PDF. Similarly, the beta parameter only changes the scale. So here I have here alpha equal to 2, and when beta equal to 1, I see this shape. When beta equal to 1.5, I see the same shape. Now x go from 0 to 10, x go from 0 to 15, so I change the scale. When beta equal to 3, x goes from 0 to 30, so I change the scale again, but I still have the same shape. And finally, beta equal to 5, I have once again the change of scale to 50, but still the same shape. So in summary, the alpha parameter changes the shape, the beta parameter changes the scale. So as the first special case of the gamma distribution, so this is a special case of gamma. We have the exponential distribution. So let x be gamma 1 beta. So now the shape parameter is alpha equal to 1 and beta as the scale parameter. Then x is said to be an exponential random variable with the rate lambda given by 1 over beta. And so usually in the exponential distribution, we usually use the rate parameter, as we make clearer in a second. Oh, before that, I just want to backtrack and say that you might want to note the following result. So, as we will make clearer in the later in the argument, so we want to state the following proposition. Let x be gamma alpha beta. Then y, which is c times x, is distributed gamma alpha c times beta. So change the scale. And you can prove this as your leisure. So by scaling the random variable x, we get a new gamma that just change the scale, which coincides with what we described it here. Okay, so let's go back to the exponential distribution. So the exponential distribution is a gamma distribution with shape alpha equal to 1. So because of the general gamma distribution, the PDF is x to alpha minus 1, e to minus x over beta, and so then divided by gamma of alpha, and then beta to the power of alpha. So in this case, because alpha equal to 1, gamma of 1 equal to 1. So you don't have that 1. And then use the parameterization 1 over beta equal to lambda, you will have the appearance of lambda and e minus lambda x. So that is why the PDF for the exponential is of this form. So this function turns out to be easy to integrate. So therefore, you can have the cumulative CDF, which is this term here, which is just the integral from 0 to x of the PDF. And this integral turns out to be very simple, as you can check. So everything from 0 to x of this function, that's just 1 minus e minus lambda x. So we have a closed form for the CDF. As we see later, this is one of the few special cases of the gamma distribution with a closed form for the CDF. So using this fact, the tail property, which is 1 minus the CDF, is now of the form e minus lambda x. And because of this simple form for the CDF, you can also get the quantized function. So what we have is that 1 minus e minus lambda x is equal to p. This implies that x is, which is equal to f inverse p, would then be equal to moving this to the other side, 1 minus p, take the ln logarithm, divide by lambda, and then, equal to minus of ln 1 minus p divided by lambda, which is what we saw here. So because of the simple form of the CDF, we have a closed form expression for the quantized function of an exponential random variable. And in particular, we can easily see that the median is equal to 1 over lambda times minus of ln 1/2 for the median of the exponential random variable. So the nice thing about the exponential random variable is that it relates to the waiting time of a Poisson random variable. More specifically, suppose we consider the following case. We're interested in modeling x, which is the waiting time until the first occurrence of some particular event. And so suppose we model that on average, lambda of these particular events happen during 1 unit of time. Say, over a span of 1 hour, on average, 3 buses comes. So what is the waiting time for the first bus if you show up at the bus stop? So then the question is, what is a reasonable distribution for this waiting time x? And the idea turns out to be simple as follows. Suppose that you have x, little x bigger than 0, which is denotes some value of the waiting time. So now let's think of z subscript x, which denotes the number of events appearing during this time interval from 0 to x. Now, because lambda is the rate for the interval 0 to 1, so if you have the interval 0 to x, you will just get rate, which is lambda times x. If you assume that a Poisson model is suitable, that is why you have this Zx Poisson lambda x as a plausible model, or maybe a first approximation to the random variable, to the model that best describes Zx. So now the key point is that if your waiting time is bigger than this little x, then that means that from the time 0 to x, there are no event, in which case Zx is equal to 0. If you have to wait longer than x, that means from the time 0 to little x, there are no events, so Zx equal to 0. So therefore, the property that capital X bigger than little x, the same as the property that there are no events between time little 0 to x, and that is simply E minus lambda x for the PMF, the property mass function of a Poisson random variable with rate parameter lambda x. And so therefore, you can have the CDF can be written in this form, and this is nothing more than the CDF of an exponential. So there should be a lambda here. That's a typo, 1 minus lambda E minus lambda x. So I will try to fix the typo in the lecture note, but there's a typo here. So like we said, that is the CDF for an exponential random variable. And so please see problem 4.168 and 4.1.73 in your textbook that kind of go through the same derivation. So like we said, the exponential random variable is commonly used to model the waiting time until something, say the first failure of some equipment, of some machines. And in that case, then the parameter lambda refers to the failure rate. So the larger the lambda, the more frequent the failures, in which case, due to the scale parameter, the beta will become smaller. And as we'll see later, the mean of E exponential is 1 over lambda. So exponential, the exponential of x is 1 over lambda. So what that meant is that the larger the failure rate, the smaller the expected waiting time. So one other nice property of the exponential random variable is that it is memoryless. So if you remember from your discrete random variable class, that the geometric is also memoryless. So let's write it down. So geometric random variable are memoryless in the discrete case. So the exponential here is memoryless, which is the analog of the geometric, but in this case with a continuous random variable. And so what that meant is that the probability that you have to wait for more than t plus s time unit, given that you already wait for t time unit, that is the same as a property that you have to wait for s time unit starting from the beginning. So even though you have already waited for t time unit, that doesn't change the fact that you have to wait for another s time unit. And both the answer is E minus lambda s. And this proof follows directly from calculation. So we know the property of x bigger than t plus s, given that x bigger than t. So that's the property of the intersection. So that means that x bigger than t plus s, divided by the property of this lower event. And as we recall, the tail property here, this one here is a tail for this one, and similarly for here, and simple manipulation gives you E minus lambda s, which is the tail property for x bigger than or equal to s. So you can show a bit at a slightly more complicated argument that the exponential random variable is the unique random variable in the continuous case that has this memory rest property. If we recall, the geometric is the unique one in the discrete case. So that's why these two are very closely related. Okay, so now starting from the exponential random variable, we can define other more complicated random variable. So the first case is, let's think of a sum of independent exponential random variables. So if you think of x1, that's the waiting time until the first event. If you think of x2, that's the waiting time from the first event to the second event, and so on and so forth. So you can think of x here, which is the sum of x1, x2 up to xm, as the waiting time until the occurrence of the mth event. So as you can say, this sum of random variables turns out to be a gamma random variable with shape parameter, which is m times, so that's m times 1, because each of these is gamma 1 and say lambda. So the shape parameter becomes m, but the rate parameter stays the same. So a sum of exponential, independent exponential, turns out to also still be a gamma random variable, with the shape parameter properly changes, but the scale parameter or the rate parameter fixed, stays the same. So the proof of this is as follows. Because we say each of the xi is the waiting time until the first occurrence of event, we can view the sum as the waiting time until the occurrence of the mth event. So now let's give you a x bigger than 0, and let's consider the property that capital X is bigger than little x. So once again, using our favorite trick, which is the Poisson random variable, let's think about Zx, the Poisson random variable, for the number of events during the particular time interval 0 to x. So once again, that is just Poisson with rate parameter lambda x. So now if you have to wait more than x time point to have the mth event, then that means that from the time 0 to x, you only has at most m-1 events. So if you have to wait longer than little x, then that means from time 0 to little x, you only have at most m-1 events. So therefore, that is Zx less equal to 1 m-1. And because this is a Poisson, you can easily see that you can easily find the CDF for this Poisson. So the property that capital X less than little x, which is now equal to 1 minus the property that x is bigger than or equal to x. So that's the same as 1 minus the property that the Poisson is less than m-1. But we know that this probability for the Poisson is very easy to determine because we know the PMF for a Poisson lambda x, which is given here. And so you have this expression for the CDF. So this is the CDF of capital X. And so given the CDF, you can easily determine the PDF. So given CDF, take derivative to get PDF. And that's what we say, right? Because f of x is integral from negative infinity to little x of little fx dx, which is the PDF. So if we take the derivative of the CDF, taking the derivative of the CDF with respect to x, so that's the derivative here. And the derivative of a sum is a sum of the derivative. And now the derivative here you can easily compute to be the first term if you take the derivative with respect to e, the exponential. And if you take the derivative with respect to the second term, which is lambda x to the power of I, you get this term. You can split this out into two parts. The first term here goes here, and then the second term here goes here. So now let us do some simplification. So let us look at this two term here. So the first term is what we have here. Now if you look at the second term, it looks almost the same, because you have the I here. If you normalize by I factorial, you then will get this term is just going to be e minus lambda x, lambda to the power of I, x I minus 1 divided by I minus 1 factorial. And this is I factorial. So you can re-parameterize that, so that instead of going from I from 0 to n minus 1, you now sum from I from 0 to n minus 2. This is now a telescoping sum, so the difference here is just the term equal to n minus 1. So this goes from 0 to n minus 1. This goes from 0 to n minus 2. They all look the same except the summation index. So you have the final term is just this term. And this looks exactly like the PDF of gamma and lambda. And so we have what we want: shape parameter m, rate parameter lambda. So a gamma random variable with the shape parameter alpha, where alpha is a positive integer, that turns out to be known as the Erlang random variable. And the name Erlang just means a sum of independent exponential random variable. So the exponential Erlang serves as the continuous analog of the geometric and the negative binomial. Because as you recall, the negative binomial is the sum of independent geometric. And with this final result here, we can say that in the case when alpha is a positive integer, there is a simple formula for the CDF. And that simple formula is given here. This formula here. But in general, there is no simple formula. Like we said, except in the case of alpha being a positive integer. So let us use this characterization of the exponential and the Erlang to solve the following problem. Suppose I have an electronic component, and that the lifetime in hours of this component turns out to be possibly modeled as a random variable with this PDF. So this is the PDF for the exponential random variable with rate lambda equal to 1/100. So now suppose that I have 3 of these components, and that 3 of these components operate independently in a piece of equipment, and that the equipment fails if at least 2 of the components fail. Okay, so find the probability that the equipment will operate for at least 200 hours without failure. So the failure rate is 1/100. So what is how long will it work? What's the likelihood that what's the probability that it will work for at least 200 hours? So because each component is exponential, and I have 3 components, and I'm interested in failure of 2, so this seems to be modeled as a Erlang with shape parameter 2. Okay, so because x is exponential 1/100, so if we let z be the waiting time until the second failure, because if I fail for 2 units, I can't work anymore. We're interested in the probability that z is bigger than 200, and now z is an Erlang random variable, which is say shape parameter 2. So if we let W be the random variable modeling the number of failures during time 0 to 200, then as we say earlier, if the failure time is larger than 200, then there are at most one failure between time 0 and 200. And that is given by this term, which is the PMF of the Poisson with now lambda times 200, which is Poisson of 2. And so we have these two terms here, and simple summations turn out to be roughly 0.406. So this is a typical problem in many of these kind of like reliability study. You're given a failure rate for a single component, and you want to see what's the failure rate, how long you have to wait before, say, k components fail. So as another example of E gamma is the chi-squared distribution. So the chi-squared distribution, once again, has this m bigger than 0 parameter. Then if given m bigger than 0, if I have a random variable x that has shape parameter m over 2 and scale parameter 2, this is known as E chi-squared. And the PDF of this chi-squared with this m degrees of freedom is given by this prototypical example of the PDF of a gamma. So we will usually denote a chi-squared random variable as x chi-squared m symbol here. As we'll see later in ST432, we usually choose m to be a positive integer. But this is not required because this is well defined even for non-integer m. So well defined for any m bigger than 0, not necessarily integer. So when m equal to 1, which is a very special case, this PDF here is of this form. And this refers to the fact that gamma 1/2 equal to square root pi. So see your earlier lecture notes. Or see your lecture notes. See the earlier slide. See earlier slides. Okay. So the chi-squared distribution is a very special case of the gamma. It's special in the case that you use the scale parameter equal to 2. So it turns out that there is a very interesting relationship between the chi-squared and the normal. And that is given by problem 6.7 in your textbook. So if z is standard normal, then z squared is chi-squared with m minus 1 degree of freedom. So a chi-squared with 1 degree of freedom is the square of a standard normal. So here is problem 6.7. So you may say, well, we are only at chapter 4. But it turns out that sometimes using some of the subsequent material is useful enough. So we won't care too much that we are going a little bit ahead. We'll revisit this concept later when we talk about chapter 6. But in any case, we will derive the PDF for a chi-squared as follows. So because z takes on both positive and negative values, z squared is not a monotone function of z. So the monotone transformation rule earlier does not apply. Okay? So we cannot directly apply the result for the monotone transformation because z is not monotone. So nevertheless, z squared is monotone for positive z and is also monotone for negative z. So what we then have is that the probability that x squared less than little x, where x is z squared. So this has to be, this is a typo here. This has to be probability that x less than or equal to x, which is probability of z squared less than or equal to x. And because it is not monotone, you have to replace it with this probability. So if it was monotone, you will have, if z squared was monotone, it will have be equal to probability that z less than or equal to square root x. But because it's not monotone, you have to truncate it at minus square root of x. And because z is standard normal, so this is given by the difference of the CDF of a standard normal. So like I said, phi is a CDF for standard normal. So now, once I have the CDF for x, I can just take the derivative with respect to little x to obtain the PDF. So taking the derivative here, that's easy, because this one will just becomes the PDF, so that will be just becomes 1 over 2 times square root of x times the PDF, which is now e to the minus square root of x squared divided by 2. And then for this term, that's once again, you will have minus, this is a minus, so that's minus of minus 1 over 2 square root of x, and then e minus square root of e to the minus of minus square root of x squared divided by 2. In both cases, is e minus x divided by 2, and then you have this one here. Oops, you have to introduce times 1 over square root 2 pi. And then here also 1 over square root 2 pi. But that doesn't matter because of these 2 here cancelling out. So you get the remaining of 2. So in summary, the chi-squared with 1 degree of freedom is the square of a standard number. So now we will come to computing the moment generating function of a gamma random variable. So let x be gamma alpha beta, where now we use beta as a scale parameter. Then the moment generating function for x turns out to be given here. And we note that this is only defined for t, absolute value of t less than 1 over beta. So not for all t. Okay, so we require that the absolute value of t is less than 1 over beta. And the proof of this is as follows. So we recall that this is something we talked about earlier slides. That due to this form for the PDF, that integration has to be gamma alpha beta to the power alpha. Then if that's the case, then the moment generating function follows directly from this result with a slight change of variable. So here we have the definition, the moment generating function, which is the expected value of e of tx. And we have this 1 over gamma alpha beta alpha in the PDF. Now we have e of tx, and this is the remaining term in the PDF. And then now I can move e of tx with the term e minus x over beta to get this term. And I want to write this in the form that after moving, so 1 over beta minus t is the same as 1 minus beta t divided by beta. So I have this term here. And this is once again, so now we have x times 1 minus beta t divided by beta is nothing but that x divided by beta divided by 1 minus beta t. But if we use that form, we see that by looking at this integral here becoming gamma alpha, beta alpha, that if we use beta, if we have beta prime become beta over 1 minus beta t, then that becomes this term here, which is beta prime. And so we have this term originally here, which is here. Therefore, this integral here, the numerator is this integral here. The numerator okay, so this is the numerator here. Yep, the numerator here is this integral here. And so after some simplification, we get this expression here. So as we can see, the moment generating function for a gamma random variable turns out to be quite simple. The scale parameter appears here and the shape parameter appears in the exponent. So the reason why we require that absolute value of t is less than 1 over beta is just simply that in order for this integral to be finite, we require that this exponent here has to be negative. So we have to think about e to minus cx, where c has to be bigger than 0. Because otherwise, the integral will be diverging to infinity. So that is only finite if 1 minus beta minus t is bigger than 0. So that's why we require t less than 1 over beta. So the nice thing about this form of the MGF for the gamma alpha beta is that it implies the following immediate corollary of a sum of gamma random variable. So this is problem 6.57 in your textbook. But roughly speaking, if x1, x2 up to xm are mutually independent random variables, each of the xi are gamma random variable with the same scale parameter, but different, possibly different shape. Then the sum is once again a gamma random variable where the shape is the sum of the shape with the same scale. So the sum of independent gamma random variables with a common scale also turns out to be gamma. So what this implies is the following nice result. Is that because a chi-squared with 1 degree of freedom is the square of a standard normal, a chi-squared therefore with m degrees of freedom is the sum of squares of m mutually independent standard normal. Because if x is chi-squared with m degrees of freedom, then x can be written as chi-squared 1 plus chi-squared 1 plus all the way to chi-squared 1. Each of these chi-squared is now a square of a normal. z1 squared, z2 squared, up to zm squared. Well, now these are independent standard normal random variable. And so you can easily show that the moment generating function for a chi-squared with m degrees of freedom is of this simple form here. And you will see this many times in ST422. So finally, as a curiosity, a chi-squared random variable with m degrees of freedom is the same as an Erlang random variable with shape parameter m over 2. Whenever m is an even number, the only thing that changes is that the scale parameter is fixed to be 2. So since a chi-squared is related to a normal, the Erlang is related to the Poisson, can you think of any explicit relationship between the Poisson and the normal? So can you go from the Poisson to the normal somehow? I have not been able to find a way to explain this relationship other than via the moment dating function. So if you can, I would be very excited to hear what you have to say. Of course, I'm excited to hear what you have to say in general, but in this case, I'm excited also. Okay, so we will soon end our lectures, but before that, let us give a formula for the mean and the variance of the gamma random variable. So the mean of a gamma, alpha beta, the expectation is just alpha times beta. And if you use the rate parameter, you use alpha divided by lambda. So here lambda is the rate. And the variance is alpha times beta square. And so this follows directly from calculations because this integrand here is nothing more than gamma alpha plus 1 beta alpha plus 1 because that is the what we say earlier in our slide. And then to go from here to here, you just have to remember the fact that gamma alpha plus 1 is alpha gamma alpha, which is also in your earlier slides. So that gives you back alpha beta. Similarly, if you look at expected value of x squared, now you have alpha plus 1 because with the normal x you have, because the PDF is x alpha minus 1 e minus x over beta divided by gamma alpha beta to alpha. So therefore, if you use x squared, you have x alpha plus 1. And this, once again, you can use the same trick in your earlier slides to get this term here, which is this term. And then finally, you have gamma alpha beta alpha for the denominator here. And using the same trick that gamma of alpha plus 2 is alpha plus 1, gamma alpha plus 1, which is now alpha plus 1, alpha gamma alpha. So this term cancels out with this term. And so you have left this expression, and so the variance is easily shown to be alpha beta squared. So a few examples. So if you have x be exponential of lambda, where lambda is a rate parameter, then the mean is 1 over lambda, and the variance is 1 over lambda squared. So as we say, because lambda is the rate of the Poisson, so what this implies is basically that larger rate means smaller waiting time until the first event. That is why in this case of exponential, the rate parameter makes a little bit more sense. Okay, because of this relationship to the Poisson. As another example, if x is chi-squared with m, where m degrees of freedom, then x is gamma with shape m over 2 and scale 2. So the mean is now m alpha beta, and the variance is alpha beta squared, so that's 2m. The nice thing, the very beautiful thing about the gamma distribution is not only do you have a simple expression for the mean and variance, it turns out you also have the simple expression for any fractional or inverse moment. So this is problem 4.111 and 4.112 in your textbook. But what we say is that if x is gamma alpha beta, then for any number c, as long as c is bigger than minus alpha, the expected value of x to the power of c turns out to be given by this simple expression here. And the key point is once again that this integrand or this integral is nothing more than this term here for this integral. And so you could simplify out. So as we said, the gamma distribution feature prominently in your follow-up class on statistics. So in summary, for the gamma random variable, you can compute any of these fractional or inverse movement. So for example, if alpha is bigger than 1, then you could just say that the expected value of 1 over x for a gamma is nothing but the gamma of alpha minus 1, beta minus 1 divided by gamma of alpha, and so that is nothing more than beta minus 1 divided by alpha minus 1. Due to the fact that gamma of alpha is now alpha minus 1, gamma alpha minus 1. And for others, and then you can think about things like expected value of 1 over square root of x and other things like that. So with that said, we will end our lecture on the gamma function here. For next lecture, we talk about the beta distribution. So I will talk to you later. Bye.